corollary is, if A be an m by n matrix and D is column equivalent matrix which is column equivalent to A, then the non-zero columns of D forms basis for column space of A. And this corollary can also be asked as, then the non-zero columns of D is equal to the column rank of A, right? So we need to show this. Let's start with the proof. Now since it is given to us that D is column equivalent to A, which means D is obtained from A by applying the column operations, right? So therefore, there exists a non-singular matrix, let's say Q, such that this D is equal to A into Q, right? Thus, column space of D is equal to the column space of AQ. And because Q is a non-singular matrix, the result is that column space of AQ is equal to the column space of the first matrix, which is multiplied with the non-singular matrix. So the reason, as Q is invertible or non-singular. Now suppose that D consists of R non-zero columns, and we have to show that these number of non-zero columns forms basis for column space of A. In the previous result, we have done that these non-zero columns forms basis for column space of D. But in this result, we have to show that these forms basis for column space of A, right? So for the basis, we have to prove the two conditions. First, these number of non-zero columns spans column space of D, and second, these are linearly independent, right? Now since D is in column equivalent form with R non-zero columns, so therefore the first R non-zero columns, that is C1, C2, C3 up to CR of D spans column space of D. This is already given, right? Second, required to prove that these number of columns are linearly independent, right? So let D matrix be equal to as Dij, right? And let L1, L2, L3 up to LR, these be the row indices of the leading entries of the non-zero columns of D, right? Then we have to define DLKJ. This represents the number of rows and this represents the number of columns. So this is equal to delta Kj, that is a Renneker delta. This we have to define, and this is equal to 1 if k is equal to j and is equal to 0 if k is not equal to j. And then we have to write the linear combinations of the columns because we need to show that these columns are linearly independent. So let's write the linear combinations of them. So I'm taking the scalars to be alpha 1, alpha 2. So alpha 1 C1 plus alpha 2 C2 plus alpha 3 C3 plus so on up to alpha R CR is equal to 0. Writing this in summation form. So now to write this in the summation form as summation alpha j Cj, where j is going from 1 to R. This is equal to 0, right? And this Cj is written as Dij because the element present in each column can be represented as Dij, right? So this implies summation j going from 1 to R alpha j. Now this Dij is written as, instead of I, I'm writing this as Lk, that is the row indices, as k is going from 1 to R, and this holds for I equal to L1, L2 or up to LR, right? So this implies this DLKJ is nothing but the Renneker delta. So writing this as j equal to 1 to R summation alpha j, and this is your Renneker delta equal to 0, and for k going from 1 to R. And because for k is lying between 1 and r, this delta kj is non-zero, so which means this alpha j must be 0 for this summation to be equal to 0. So this implies alpha k is equal to 0 for k equal to 1, 2, 3 up to r. So this implies alpha 1 is equal to alpha 2 is equal to alpha 3, so on. Alpha r is equal to 0. And because all these scalars are 0, and where we have written the linear combinations of these non-zero columns, for this linear combination all the scalars are equal to 0, which means C1, C2, C3 up to CR, these are linearly independent. This is the condition for the linearly independent C of the columns. So therefore, C1, C2, C3 up to CR, this is linearly independent. And because these non-zero columns already span column space of D, and now these are linearly independent also, so with these two conditions, these forms the basis for column space of D, right? But from here we have seen that column space of D is equal to column space of A. So if these columns, the non-zero columns, forms basis for CD, then these also forms the basis for column space of A. So, but column space of D is equal to column space of A. Hence, C1, C2, C3 up to CR, these non-zero columns is a basis for column space of A also, right? And remaining to show that these number of non-zero columns are also equal to the column rank of A. Now as these forms the basis for CA, which means the dimension of column space of A is equal to R, right? And dimension of column space of A is column rank of A. So that is equal to R, which is equal to number of non-zero columns of D. Hence the result. Thank you.